Okay, so good evening, everyone. Welcome to the online interactive lecture series that are being organized by the INO project for the last 5 weeks. In fact, today would be the 14th lecture in this series. We'll come back to today's lecture, but before that, I would like to also remind you the next lecture in this series is going to be on 29th, that is tomorrow itself, at the same time, that is at 6 p.m. This lecture is going to be given by Professor C.S. Unnikrishnan from TIFR Mumbai, and the title of his talk is going to be the spin in the difference between bosons and fermions. Okay, so that is the announcement for tomorrow's talk. So coming today, we are going to have Professor Sreerup Raychaudhuri from TIFR Mumbai going to talk on From Nano to Atto, the amazing world of elementary particles. And as it was announced, this talk is going to be in a different level where it is kind of more accessible to even more younger students than that typically has been the case till now, where the talks were actually more suitable for MSc plus students. And also you might notice that all the talks so far has been more on more closely centered on neutrinos, but today we are going to have a talk which is more centered around the spectrum of elementary particles. And the rest, of course, we'll leave to the speaker. But before I hand over the platform to Sreerup, I want to say take a couple of minutes to introduce formally to him. I'm sure quite a few of you know him quite well. Professor Sreerup Raychaudhuri is a theoretical physicist in TIFR who works on the physics of elementary particles and their interactions. He's a PhD from the University of Calcutta and worked as a postdoc both at TIFR and at CERN. He taught physics at IIT Kanpur for 9 years before joining as faculty at TIFR. His research interests are interfacing theory with experiments, especially in the physics of electroweak interactions. He's also interested, besides, of course, his work in these areas, but he's also interested in pedagogy and the history of science. Those of you who have not seen or heard his talks on history of science, history of elementary particle physics in India, and so on, Google, and there are excellent talks available on both YouTube and in general on the internet. Okay, so with those few words about Sreerup, now over to Sreerup.
Okay, let me share my screen first.
Yeah. Yes.
Okay. Okay, so let me first thank you for that very warm introduction, Satya. And to everyone, I wish you good evening and welcome to this talk. I'd like to thank the INO collaboration, in particular Dr. Satyanana, who has organized this, for giving me this opportunity to give you this talk. And as he has already told you, this talk is going to be a little different from the technical talks you have heard before. It's going to be at a very elementary level. It's meant for all, for the general public. And I did see in the list of participants that there are some real experts. And to them, I apologize. I will not be able to tell you anything new, but perhaps you will like my pictures and presentation. So let me begin at the beginning. Why is it nano to atto? So let's look at this form. Remember the SI prefixes, and you see that when you go to the smaller side, you go from deci, centi, milli, and so on. So we begin at nanometers. And then I will take you through the journey through pico, femto, up to atto. So 9 orders of magnitude down, and really how we have progressed in our knowledge from here to here will be the main theme of my story. All right. So let me begin with what I call the ancient period. So this is going to be a historical story. So we begin with the ancient period and how we went from the size of a meter, which is roughly the size of the world around us, which we are conscious of, to the nanometer scale. So since I said ancient period, let us go back 250 years before the birth of Christ, before the Common Era, to a very humble device called the check valve. So this is attributed to Ctesibios of Alexandria, the Greek philosopher. In those days, philosophers also were inventors. It was just a simple device to permit fluid to flow in one direction. So what I'm showing you is a cartoon. So imagine that this is the bottom of a cistern. And on top of that, there is a cistern. And below that, there is a pipe through which water comes in. So what do you expect? The water will come in, flow into the cistern and fill it up. Okay. Now, once you remove the pressure of the water, you remove that, what do you expect? The water will not stay in the cistern. It's going to drain out through the hole and go out. So how do you ensure that when the water comes, the cistern will get full, and then when the water goes out, is not able to go out, even when the pressure falls? Very simple, said Ctesibios. Put in a little device like this, a bit like a board pin. So what will happen when the water comes in? It will push this out. The water will flow through the hole, and enter, no problem there. But of course, you need to ensure that the water doesn't come in with such force that this object here is not totally washed out. So you use something to fix it. So it doesn't go out, but it will just stay there and allow the water to come in. What happens when you remove the pressure? Now the water will try to flow out and will now push this thing back to close that hole. Simple. Now the water stays in the cistern, it doesn't flow out. So this little instrument is known as the check valve, and it's a part of our everyday life. Well, not perhaps in Mumbai city, but all around India, with this humble instrument, which you see everywhere, which is nowadays actually a lift pump, but it's called the tube well everywhere in India. So what is there in a tube well pump? There's a little check valve here. So when you pull this out, when you pull the handle out, the water comes in, rushes in and fills this place. This moves up, it comes here. When you press this down, when you press it down, then this object, the pressure comes this way, the pressure comes down on the water, this thing gets back. It doesn't allow the water to flow this way, so the water has to flow out and out through this. And this is a device which I suppose most of us at some time in our life have at least tried once. Now, from Ctesibios, I will move to several centuries, to 1649, to Otto von Guericke of Magdeburg. You see his picture here. And what he invented was a similar pump. You see the pump here, and there's a check valve somewhere here. And the major improvement he made was by putting leather washers to prevent leakage. So that in the check valve, there's a bit of leakage around the edges. But if you put leather washers there, then there's not much leakage. So you can use it for air also. And this air pump he used in order to evacuate the air from a circle like this, from a spherical object, hollow sphere, put them together, and the air was evacuated from that using this pump. It requires quite a bit of strength, so that's why you see two strong men pulling on it. In fact, it requires considerable strength. For here is the famous experiment which he did in 1654 at Magdeburg. And you see in the center there is this sphere, and there are two teams of 8 horses each. And it took the strength of 16 horses, well, 16 horsepower by modern calculations, to overcome the atmospheric pressure and pull apart the hemispheres. So this was a spectacular experiment. But since then, people have been developing better and better pumps. But the simplest one is this thing called the laboratory air pump. So you see a bell jar here. You want to evacuate the air out of this. Attach it to this simple air pump by putting 2 check valves, one here and one here. What happens is that when you pull this handle out, a partial vacuum is created here. The air rushes in from here through this check valve and enters this. At the same time, this check valve closes. Air cannot rush in from here. So therefore, some air from here goes into this tube. When you push this back, this check valve closes. The air cannot go back into the bell jar, but it is pushed out through this check valve. So it goes out. Keep repeating the process, and at some stage, the air pressure in this is going to fall considerably. Of course, you could put the check valves the other way around, in which case every time the pressure inside this would increase, and that is an object again which many people have used. It's called the bicycle pump. Okay, so after this laboratory air pump, over the years, people began to improve the level of the vacuum you can create inside. So here I have a graph of orders of magnitude, and over the years, as you see, gradually the vacuum became better and better. Great exhibition of 1850, Geisler, Crookes, and others. I will mention these names, famous names, Edison and so on, till about 1900. And then, so the pressure fell to 10 to the minus 6 torr from about 10 torr, which is the atmospheric pressure. And then over the years, we have been going down through other methods, better methods, till by the turn of this century, we have gone down to about 10 to the minus 14 torr. And just to put this in perspective, the pressure you see in outer space, which is an excellent vacuum for all purposes, is about 10 to the minus 13 torr. So really, this business of making a vacuum has gone to great extents. And long before we reached this kind of stage, very interesting results came out of the fact that we could make vacua. In 1705, Francis Hauksbee the Elder, there were two, father and son, who were inventors of various things, but this is the invention which is actually the most interesting. Francis Hauksbee, you see here with all his wig and so on, invented something called the electrostatic glow lamp. What was the idea? That you had this glass bulb and the inside was evacuated and then the bulb was sealed. So when you could charge this, you had these two metal things around it and you rubbed them with some cloth or something and charged them. Then people found that this emitted a ghostly glow. So in the dark, it would glow with a kind of green glow. And the light was enough to read in the dark. You could put it in a dark room and it gave you enough light to read a book by. So it was something like a toy, but it was showing you that there is some connection between the vacuum and this electrostatic glow. So this set off a series of studies, maybe 100 years later, and this really arose with the invention of this object called the discharge tube. So the discharge tube was invented by, Heinrich Geisler. You see him here, Geisler, and he was actually the assistant to a professor called Julius Plücker. You see Plücker here. Of course, this is Geisler not when he was an assistant, but much later when he became famous. They wanted to investigate if electricity could pass through a vacuum. That was their real idea. So they invented this kind of a tube, a glass tube where you create a large vacuum and then you seal it. You seal it off from here, just melt the glass and seal it. And there are two electrodes at either end. You connect them across an electrostatic generator and pass current and see with what level of vacuum you could pass what level of current. And what they discovered is that if you put different gases and you pass electric current through them when the pressure is reduced, they start giving you different colors. So you see here the color of a hydrogen tube, a deuterium tube, nitrogen, oxygen, mercury, and you can clearly see the different colors. And in fact, if you put them through a spectroscope, you will see different lines of the spectrum. But that's not part of our main story here. Instead, when people took this thing further, this was done mostly by a gentleman called Sir William Crookes at London and also Philip Leonard in Germany around the 1870s. So what they did here was, you see a Geisler tube here. It's a different shape, but it's essentially a Geisler tube with electrodes. And these are connected across a primitive high voltage generator called a Ruhmkorff coil. So you must remember that AC had not been invented. So you required this instrument called a Rumkov coil, which you sort of cranked up with this handle. You see this handle here. You cranked it up with the handle and then let it go. And for a moment, there was a transient flow of a very high voltage electricity. It was basically a transformer. So what happened was that he kept reducing the pressure in the discharge tube and then seeing what happens as you let the high pressure go. So I'll show you a modern version of a Crookes tube and a little bit of video. I hope it works. Yes. So this is what happens as the pressure goes down, and you see that various phenomena start showing up. You see this is the light coming, and then you see bright spots, you see what I call striations, and in the end, the entire tube begins to glow green. So what was suggested by Eugene Goldstein at Berlin in 1876 was that this green glow is due to the fluorescence of the gas when it is struck by radiation, invisible radiation emanating from the cathode. So that was simple. They were sure that it was coming from the cathode because if you put something in front of the cathode, it didn't reach. So you see this is the same picture which I showed you, but the video. And you see that here, this is the cathode, this side, and there are rays coming out from here. But when they hit all the glass around here, then you get this green glow. Moreover, the nice thing showed by Crookes in his famous experiment, this is the same apparatus I showed you the actual photograph of, that if you put an obstacle in front of the cathode, you see here that there is this Maltese cross here, and it's a piece of metal, and it throws a shadow. So that shows you, why you have shadows, because light travels in straight lines. Similarly, you know that the cathode rays throw a shadow, a very clean shadow like this, because they are traveling in straight lines. So now you see something here more, that if you have the cathode rays, if you use a magnet, then you can deflect them. Okay, let me try to repeat that again. You see the magnet moves the. So what are the conclusions we draw from here? Okay, sorry. Cathode rays travel in straight lines if they're undisturbed. You can deflect them by an electric field. I haven't shown them, but they do get that, and they are deflected by magnetic fields. So all of these are characteristic of a stream of charged particles. So imagine there is a source here, and there's a stream of charged particles which are coming out. So if undisturbed, what would you expect? They're coming out at high velocity, so they will move in straight lines. Put them in an electric field between a positive and a negative plate, and they are deflected. So actually the direction of deflection tells you they are negative particles, which is expected since they're coming from the cathode. And put them in a magnetic field, and then you have your right-hand rule, and so they will get deflected again in the same opposite direction. Now, Sir J.J. Thomson in 1897 at Cambridge, you see Thomson here, set out to see what happens when you put these cathode rays in electric and magnetic fields which are crossed in direction. I'll show you that in a moment. This is the actual apparatus which he used. It's preserved in the Cavendish Museum at Cambridge. This is a picture which I took myself. And you see the actual apparatus. It says here, gas discharge tube with which Thomson discovered the electron. So in the background of this actual apparatus, I'll show you a sort of cartoon of what happened in his experiment. So this part had the cathode here. So let's suppose the cathode warmed up. You see it glowing green. And then particles began to come out of the cathode rays, and come and hit the tube on this side. And they created a green spot where the particles were coming and hitting it. Now, Thomson had put 2 electrodes here. So he connected them across an electrostatic generator in an electric field, and it was found that the particles are getting deflected. So they come and create the green glow, moved from here to here. Then, keeping this on, he used a magnetic horseshoe magnet to put a magnetic field like this. So the 2 ends of the horseshoe are on both sides. And of course, it deflected the things back. So he found that by adjusting the electric and magnetic field, which he could do, he could bring the particles or the glow exactly back to where it was. Now the mathematics is simple. Use the electrostatic and the magnetic force, make them balance each other, and you arrive at this equation. The charge of these particles divided by the mass of these particles is 1 by the distance. This is the distance between the place where they're coming out from and this glow, easily measurable. The electric field and the square of the magnetic field. All of these are easily measurable. And when he did that, Thomson found that for cathode rays, this E by m came to be 1760 times 10 to the 8 in some unit. Whereas when he did it in the opposite way, for hydrogen ions, instead of cathode used an anode and used hydrogen ions, hydrogen being known to be the lightest element, it was only 0.959 times 10 to the 8. So now this large ratio you have to explain. Obviously, there are two possibilities. One is that the charge on these cathode rays is many times the charge on the hydrogen ions. But if you did that, where would this extra charge come from? Because they are coming out of atoms. An atom contains, well, not so much of charge. But where did this huge amount of charge, if it came out of atoms, then the atoms themselves would become very highly charged with the opposite charge. But they remain more or less neutral. So it's unlikely that a huge amount of charge is coming out. So it's reasonable to assume that the charge here is the same or similar. So in that case, this m must be much smaller. So therefore, the cathode ray particles must be around 1836, that's the ratio here, times lighter than the smallest atom. And therefore, Thomson became the discoverer of this little particle, which was smaller than the atom and which we now call the electron. Again, he found that whatever you made the cathode out of, the electrons were the same. They had the same E by m. So it was clear that atoms all kinds of atoms have electrons in them. So the original picture of the atom, as imagined by Democritus long ago, and by John Dalton in the early 1800s, which leads to most of chemistry, was as a sort of solid sphere, but this was not true. The atom actually has structure. There are things inside the atom. And I would think that this is perhaps one of the greatest discovery of modern times, at least in physics. So the next, in fact, the electron was the first elementary particle to be discovered. And we now have immediately had this picture of the electron somewhere around the atom. So there's some positive charge somewhere, and this picture of electron somewhere. You don't know more about that. So the size here is about 0.3 nanometers. So we had now jumped from the meter size, which I had mentioned when we talked about check valves and so on, meters, few centimeters, and now down to about the nanometer size. So down by 9 orders of magnitude from the meter. Now, this is the scale at which chemical reactions take place. So you can look at this little cartoon of a chemical reaction. A set of atoms come in, bunch. There's some rearrangement of atoms, and you get a new rearrangement, which gives you two new metals. This is the ammonia molecule, and this is, I'm not quite sure what it's called, but you see this reaction. Okay, so that's how chemical reactions happen. And of course, with the different kinds of atoms, we now know how to put them in the periodic table. You also know that Niels Bohr, that this periodic table discovered by Mendeleev, Niels Bohr devised a method to explain this periodic table in terms of the way in which the electrons are arranged in that elements. So with this discovery, I would say the ancient period end, and now we come to the Middle Ages, how we move from the nanometer to the femtometer scale. Now, I'm going to show you this. This started with the discovery of radioactivity. And you see here a picture of a radium dial. I think nowadays people put glowing dials, but no longer radium because it's known to cause unhealthy. But for a long time, at least even in my childhood, we used to wear watches with radium dials. Many people listening to me will remember it. And here are some of the people who made the major discoveries here. Becquerel at the top, who made the original serendipitous discovery of radioactivity. The two Curies who took it ahead. Fahans and Soddy, who understood the radioactive displacement law. Willard, who discovered gamma rays. Rutherford and Royds, who discovered alpha rays. And finally, Becquerel was the person again who discovered beta rays. I'll come to that. But these were the main heroes and one heroine who discovered that. Now here is the simple experiment which Rutherford and Royds performed back in Canada, in Montreal around 1900. So the idea is the following. You have this little lead chamber, and there's a cutaway here showing you that there's a radium pellet inside it. And you have a screen in front with a hole in it so that anything which comes out of this will be directed along this hole. There's a screen here, which if a charged particle or any high energy particle hits it, this screen is going to glow. It'll give you a green glow like you saw on those tubes. And you put the whole thing in a magnetic field going into the plane of the paper of the screen in front of you now. So what you do is you open the screen. The moment you open it, you see that there is not one glow, but three glows. If you remove the magnetic field, there'll be a glow only here. But if you keep the magnetic field on, there'll be three glows here and here. So what is that telling you? It's telling you that there is one kind of particle which is coming out and getting deviated like this. These are the alpha rays of Rutherford. Another kind of particle which comes out like this. These are the beta rays, which Becquerel, you see Becquerel now when he was much older and actually made this study. And there is a third kind of ray which is not deviated at all. And these are the gamma rays which were discovered by Wheeler or identified by Wheeler as electromagnetic radiation. So this is the beautiful separation of radioactive emanations into alpha, beta, and gamma rays, and the lovely experiment which was done to do this. Now, the standard picture you see in all textbooks was actually devised in this particular book. This was the doctoral thesis submitted by Madame Curie, and there she drew this picture: alpha rays, beta rays, and alpha, beta, and gamma rays. And this is the sort of picture, slightly better drawn perhaps, which you now see in all the textbooks. So it became clear that atoms have some internal structure and that the radioactivity which people were seeing was just atoms that were spontaneously breaking up. So what you saw here was atoms, and they have a structure. So the first person to try to understand this structure was the same Sir J.J. Thomson, who had discovered the electrons. So the way Thomson imagined it was that the atom is a sort of jelly, this orange jelly, orange or golden colored, sort of positive jelly. He didn't understand what it is, but it's just like a jelly. And then the electrons are embedded in it. So Thomson, based on his culture, called it the plum pudding model. Okay. Now, I'm not sure how many people listening to me have ever seen or eaten a plum pudding. It's not very common in India. But of course, you have eaten these big laddus. And inside a laddu, there is kismis placed in various places. So imagine the electrons to be the kismis and imagine the rest to be the laddu. So that was the Thomson model. So let me call it the laddu model. Now, there is a problem with the laddu model, which had based on a theorem pointed out by the Reverend Samuel Earnshaw, who was a priest who also dabbled in mathematics and physics. And he had pointed out that you cannot keep static charges in equilibrium. They are bound to move. Okay, and that's a nice thing which people learn in electrodynamics. It's a very beautiful theorem based on the mean value theorem. Now, if that is so, what would happen with the Thomson atom is that every electron would attract the positive charge close around it. So what you would have is the jelly would condense into little bits around those, and it would all get absorbed, and instead of having one atom, you would have a bunch of little neutral particles. So every atom would then degenerate into this sort of tiny things. And that doesn't happen. The atom remains at that size of a nanometer. So what could be the solution? A solution was suggested by the Japanese scientist Hantaro Nagaoka in 1903. And what Nagaoka said is that, okay, you have to beat Earnshaw's theorem, you need to assume that there is dynamical equilibrium and not static equilibrium. Now, this is what happens with the rings of Saturn, for example. You see the rings of Saturn move around Saturn, and the centrifugal force prevents them from falling into Saturn. So Nagaoka's atom, which he called the Saturnian model, he imagined the electrons forming a sort of ring around the central nucleus. So it was, you see, modeled very closely on Saturn. And then there was this jelly but the electrons were not embedded in the jelly. They were moving around the jelly, and there was centrifugal force, some angular momentum, which took care of preventing them from falling in. So, okay, nice idea. Just to remind you, it's still 0.3 nanometers. Now, Rutherford, with his assistant, this is Rutherford as he was when he did the experiment, with his assistant Geiger and another student called Marsden. So Rutherford, Geiger, and Marsden, they did this experiment to find out how to, where the positive charge is. And you see, it was a small laboratory experiment. This is the real, the real critical part which they studied. This is where they put this is basically a pump which evacuated this. And then there was an alpha source inside that. And here is a microscope through which they could look at what is happening. So let me show you once again a little bit of an animation of this. And you see the positively charged particles from the radioactive source. And they come out, and here is the fluorescent screen all around. So if there's nothing, you see this glow here. Now, if you place a gold foil in between, gold is very, very, very fine. So see what is happening. Most of the particles are going to the center, but some are going back. So let me just repeat that once again. I'll remind you that gold is, why choose gold foil? Because gold can be beaten into very, very fine foils. It's about a few, maybe 100 or 50 to 100 nanometers thick. So maybe some 100 atoms instead of a thicker thing. And alpha particles should be able to pass through that easily. Now, if you have a jelly model of the atom, then the alpha particles should simply punch through them easily and would only reach the other side, which is what is happening in this initial picture. But when you put the gold foil, then of course that's mostly happening. Most of the particles are going through, but you see some particles are deflected more, and there are a few particles which are going right back. This should be happening. So this is what Rutherford found. This is a simulation, of course, of the data. Most of the particles, imagine that you've opened out that circular strip and made it flat. And then what you would see is that the regions which are at 0 degrees, which is right in front of the gold foil of the scatterer, do get the maximum intensity of particles, but there are some which are scattered around, and some which are even going to very high angles, okay, almost to 180 degrees. They can't go right to 180 degrees because you have to leave an opening for the particles to come in, but very close. Now, you imagine that this is exactly like you have sacks full of straw, and you have a guy who is shooting with a rifle, maybe good high caliber rifle at them. What should you expect? You would expect that the bullets would simply go through. All the bullets would be on the other side. Now, if a bullet bounces back at you, then there must be some hard object inside the sack, like a stone, for example. So therefore, in the case of alpha particles, that hard object must be a high concentration of positive charge, which is repelling it and pushing it back. And so Rutherford came up with this idea. In fact, Rutherford's own description was even more dramatic. He said it was like I was firing a cannon at a piece of tissue paper, and then a ball bounced back at me. So that's how taken aback he was to see the particles coming back. So he concluded from this that the positive charge in the atom is not a jelly like Nagako had imagined or Thomson had imagined, but it's concentrated in some very, very small central point. And that is such a high concentration, high density of charge that if one of the alpha particles happens to go near it, then it will be deflected straight back. You know, it's like hitting a stone and bouncing back. So if this is 0.3 nanometers, this is far, far smaller than a nanometer. And in fact, from the experimental data, he concluded that this must be smaller than a femtometer. So at one jump, you went from a nanometer, well, maybe 30.3 nanometers. So almost 5 orders of magnitude were jumped. And then the atom, in fact, he said, is in a state of dynamical equilibrium, like the planets in the solar system go around each other. And it soon occurred to him that, of course, like the planets, they don't all have to be in the same orbit. They can be in different orbits. They don't even have to be in different planes. And so here is a picture of the scattering angle graph from a Rutherford scattering. And therefore, from here, this graph is actually fitted so beautifully by the experimental points. The theory is what happens when you have a point particle below 1.7 femtometers. So at one jump, Rutherford took science from the scale of 0.3 nanometers to about 1.7 femtometers. This is sometimes dramatically described as saying he had split the atom. The atom was, of course, already known to be split, but he really found out a very important thing about its structure. Soddy's discovery of isotopes showed that the masses of the nuclei of heavy atoms were essentially integral multiples of the mass of the hydrogen nuclei, which is the proton. So therefore, it was natural to assume that the heavy nuclei were made up of protons. So therefore, for example, you take the nucleus of tin, which has a mass number of 114. So by this theory, it must consist of exactly 114 protons. But 114 protons would have an atomic number, or which is the charge of the nucleus, of 114. But the nucleus has a charge only of about 50 times the proton charge. And we know that from its extra spectrum. And then that means that some 68 units of charge are missing. So what could this be? So Madame Curie suggested the idea. She had a good nice suggestion. She said maybe the electron, there are 68 electrons somewhere inside the nucleus. So the electrons and the protons somehow form some kind of bunch inside, and the charge, negative charge of the 68 electrons cancels the charge of the protons. And also, she had a good explanation. She said, look, there is beta decay where electrons come out of the nucleus. So those must be those electrons. Now, Rutherford had a different model. He basically thought that it was the nucleus is a repetition of his model of the atom. So it's like a little atom. Instead of having a positive charge and electrons around it, he felt there's a small negative core. So this negative core would be the 68 electrons, and then there would be protons all around it, and that would be shielding it. So there were 114 protons, and this negative charge core would be minus 68, and that would give you the. So it was sort of little baby atom inside that was his idea of the nucleus. But in 1927, when we had the uncertainty principle, it's an easy calculation to show from there that the electrons inside the nucleus would have far too much energy to be held there, and they would also have far more energy than the beta rays have. So therefore, it can't be, and the only possible solution was suggested by Ivanenko in 1927. And Ivanenko said that you have protons, but the remaining 68 are just neutral particles with a mass similar to the proton, but which are electrically neutral. So that you have only 50 charged particles inside the tin nucleus, and the remaining 68 are neutral particles with the same mass as the proton. So he managed to predict what Rutherford had already called the neutron. And in the same year, and 5 years later, in 1932, James Chadwick, whom you see a little picture of, was able to actually discover the neutron experimentally. So this led to the picture we see today. We have today, imagine the red balls here you see as the protons, and the blue ones as the neutrons. So this is the proton-neutron model of the electron, which is now there in every undergraduate or even school textbooks. Size, about 4.5. For the tin nucleus, it's about 4.5 femtometers. So we have moved from a meter to a nanometer, and now down to a femtometer. And all this happened maybe around 1930, in the 1930s. So almost 90 years ago. So in 1932, life was simple. There were only 3 elementary particles, the electron, the proton, and the neutron. There were 2 basic forces. There was gravity, of course, discovered by Newton. And there was the electromagnetic force, which many people had studied. But soon complications arose. Same year, Werner Heisenberg asked a simple question. Positive charges repel each other. We all know that. Neutral particles neither attract nor repel. So how come the nucleus is not flying apart? Okay, why are these positive protons not pushing each other apart? So what is holding the nucleus together? So he concluded that this cannot be the full story. There must be forces, attractive forces between protons and neutrons, and these are the ones which hold the nucleus together. Moreover, since you don't see those attractive forces in our daily life, these forces must be effective only at the femtometer scale. So they are what you call short-range interactions, working only at the femtometer scale. The electromagnetic interaction also works at the femtometer scale. It's very strong there. And these two forces, the repulsion, electrostatic repulsion between the protons and the attraction due to this whatever unknown interaction, these are balancing each other, which is why the proton is stable. And this force we now call the strong interaction. It used to be called the strong nuclear interaction. Now we just call it the strong interaction. And this was sort of discovered by Heisenberg. Now, 3 years later, Yukawa tried to give a free theoretic model for this. So the idea was that the strong interaction between the protons and protons, neutrons and neutrons and protons and neutrons, they must be due to exchange of a new particle which has a mass around 200 electron masses. And this he called it the mesotron, but today we call it the pi meson or the pion. Now the idea is based on electromagnetic theory. In electricity magnetism, when we have a positive and negative charge attracting each other, we believe that they are exchanging photons, exchanging virtual photons. And Yukawa based himself on that. And the fact that the particle has mass, photons don't have mass. The fact that these particles have mass explains why this interaction is short range. So this pion basically keeps these two nucleons, the proton and neutron, let us say, together, very much like these two dogs you see in the picture. So imagine the rope. None of the dogs wants to leave hold of the rope, but suppose you couldn't see the rope. What would you say? You would say the dogs are great friends and they're just going around together. But in actual fact, they are just bound because none of them wants to release the rope. So the pion is that rope, and these two protons on this side are the two dogs. So that's why the nucleus stays together. Now, how to find this hypothetical particle? Okay, it's a good theory, but we have to find it. And how to do that? So now let me take you to a different story. And here I'll take you back to 1911 and to an instrument called the cloud chamber, which was invented by C.T.R. Wilson, Charles Wilson, whom you see here in the picture. And basically the idea is you have a sort of box with the gas at a reasonably, even air at a low pressure, but with water vapor in it. And there's a bit of a small box here with a radioactive substance inside and a little hole at the top for it to come out. I've used this again and again. So what you do with this box is you take a slab of dry ice and you bring it under this. Dry ice is solid carbon dioxide, minus 78 degrees centigrade. Hold it under the box. And then you, at the moment when you are ready, you bring this box up and you put it in contact with the box. What would happen? The air inside gets cooled dramatically and fast. And you begin to see the tracks of the alpha charged particles which are coming out from this alpha. And these will start leaving tracks here, which are due to the fact that charged particles leave nuclei of condensation, and the water vapor inside tends to condense around those nuclei. So all you now do is bring a camera here and take a photograph. And in fact, here is the photograph taken. This is the same bigger blow up of the same thing which is inside. Here is an actual photograph taken by Wilson from his cloud chamber, and you can now see the tracks of those alpha particles. Now, this was a huge improvement because in all the experiments I showed you before, you could only see the source and you could see the final end point where the particles went. But now you could see exactly how the particles were going, and you see that they are bending. They are not going in straight lines, they are bending. That's because this whole thing was placed in a magnetic field. So you can remove the magnetic field and see that they're going straight. You can put back the magnetic field, and the more the particles bend, the more is their E by M ratio. So lighter particles are going to bend more, heavier particles are going to bend less. More the charge, the more the particle will bend. Most of these are singly charged, but you can make that all out from the tracks. Now, this cloud chamber was used for various things, and it was actually used also for certain discoveries, but it was replaced by better technology later. But Wilson's instrument certainly was the first to allow us to see particle tracks. Now, Victor Hess, next year, he took electroscopes high up in the air using balloons. You see Hess here descending from one of his balloons, and here are a lot of small boys. This was in Switzerland. So all the boys have collected around to see what is this strange object coming out of the sky. They're naturally like small boys are. They're curious to know what's happening. And if here is Hess and his assistant in the basket of the balloon. And what they did was they carried electroscopes high up in the air, and they found that there is charged particles are coming in the air, and so he discovered cosmic rays. For about a quarter of a century, nobody understood where cosmic rays came from. And then in the 1930s, 1920s, Skobelzin was the first to look at cloud chamber tracks of these, and he concluded from these tracks, similar tracks, you see these circles. All these circles are caused by electrons in the magnetic field, and they have been deflected so much, the curvature is so much that they've gone into these spiral tracks. And what happens is the electron goes into a spiral track, and as it loses energy by collisions with other atoms inside this material, it generally spirals in and just stops at some point. But here you could see only the first track because the sensitivity of a cloud chamber is low. Homi Bhabha and Walter Heitler in 1936, they understood what cosmic rays are. They realized that cosmic rays are really high energy charged particles bombarding the Earth's atmosphere. These come mostly from the sun. They are mostly protons coming out from the sun. But there are also some of higher energies which come from the cosmos. They come from very violent events in the cosmos, like collisions of galaxies, supernovae, quasars, what are they called? These supermassive black holes. So some of these exciting things, some of them also, they emit these very high energy particles. They come and hit the atmosphere. So basically they interact with the nuclei of oxygen and nitrogen, which are in the atmosphere. They hit those nuclei, and when they hit those nuclei, there is a lot of energy in them, so that energy gets converted into particles, and we have a shower of particles. So all kinds of particles will be created in these cosmic rays. So what they pointed out was take a balloon, fly it into the upper atmosphere as Hess had done, put a cloud chamber somewhere in that, and keep taking photographs. You could do it remotely. You could actually go up physically and do it. In the beginning, people went physically, and then later people learned to do it remotely by radio control. When you have taken enough pictures, bring your balloon down, take out the plates, and you have a free laboratory for particle physics. The cosmic rays are always there, always available, no cost. You have only the cost of sending up the balloon and developing the pictures. Now, let me take up this issue of why we are worried about high energies. So high energies are the following reason: because interconversion of matter and energy is possible, thanks to Einstein's famous relation, E equal to mc squared, which everybody knows about. So, in principle, if you have a particle with a lot of mass, this particle could go into lighter particles with a lot of energy. And similarly, the two lighter particles with a lot of energy could coalesce together and give you a particle with heavy mass. So let me take this back. So you could have a lighter particle. You see here the conversion of mass into energy, and you see here the conversion of energy into mass. So both will happen. So you said, okay, maybe you'll be creating a lot of pions in these cosmic rays, so just go and look. And in fact, not just pions, they were certainly found, but a host of new elementary particles were discovered in the cosmic rays. First the pion, the kaon, and then different kinds, delta, lambda, sigma, a whole series. For almost every year, a new particle was discovered till the mid-60s. So the situation was a bit like chemistry before the advent of atomic theory. Instead of 92 elements, we had more than 100 elementary particles, and by today we have more than 300 elementary particles. Now that's an impossible situation. Enrico Fermi, he had this comment that if I was able to remember half of the names of all these elementary particles, I would have become a botanist. And physicists look for unity. So he was really frustrated, as were many other people at that time. So the basic question was that do we have so many elementary particles to work with? It makes life very difficult. And that discovery brings us to the modern age, from a femtometer to the attometer. So now, how to determine if the protons and neutrons are elementary or are made up of smaller particles? There are two ways. There's a theoretical way, which is the way of the periodic table. Look for patterns in the properties of elementary particles. And if you have patterns repeating, then there must be substructure inside. The other is the direct way, the way used by David to conquer Goliath. Throw something, smash these particles together, break them up and see what happens. So let me describe both of them. In the theoretical way, 1957 was done by these two gentlemen, Murray Gell-Mann, who passed away very recently, Yuval Ne'eman, who's still very old but still alive. They've said that just as you can classify atoms by the atomic number and mass number, protons can be classified by two quantum numbers called isospin and hypercharge. And when you do that, you find that particles which are called the baryons, which are fermions, and include the neutron and proton, you can put them in a sort of hexagon like this with two things at the center. So there's an octet of baryons. And then there are particles called the zero-scalar mesons, which include the pions, the three pions in the central line, kaons. And then when you put them together, lo and behold, they form exactly the same kind of structure of this way. There are also the vector mesons, and you can put them also like this. They include the rho meson and others. Now, this cannot be an accident, and therefore, this repetition must correspond to repetition of some underlying substructure, just as in the periodic table. By 1964, Gell-Mann and George Zweig, both of them had come up with the same suggestion. Actually, you are seeing this repetition because every baryon is made up of three smaller particles, which Gell-Mann called quarks. And then he said every meson is a quark-antiquark pair. So you see here, the proton consists of two U-type quarks and one D-type. The neutron is two D-type and one U-type quarks. And the pion is a U and is a charged pion, a U and a D bar, an antiparticle of the D quark. And these are bound together by the strong force, which means exchange of particles, which were called, for obvious reasons, they glue the quarks together, they are called gluons. So this is how you imagine the same octet, which I showed you, the proton, neutrons. You can just put them, and there's a third kind of quark called the strange quark, which gives these a property called strangeness. Now, of course, to look at these in the experimental way, first idea is to look at the cosmic rays. But the problem with cosmic rays is that the flux falls very fast as the energy grows. So you see here, as the energy grows, and you see how the flux falls. That means that the number of cosmic ray events you will get becomes rarer and rarer as you go to higher and higher energies. So if you go a little high, the energy really falls dramatically. And then when you want to go to really high energies, this is the kind of energy you are going to look for to see these objects. So then at that point, the flux is really down to 10⁻⁻1 per square meter per second, and then you're down to 10⁻⁻10. So therefore, doing an experiment really requires either you have to make a huge surface or you have to wait for a really long time. Both of them are difficult. So the question is, there are just too few, you must either wait for years' results. So the question is, could we create cosmic rays in the laboratory by using more with higher energy? So the answer is yes, and that brings us to the particle accelerators. Here is the first one, the cyclotron devised by Ernest Lawrence in 1934. This is the real cyclotron next to a dime, 10-cent piece of that time. It was a really tiny thing. And of course, we know that when a charged particle goes around, this is not the pion, this is actually pi, close to 22/7, mass by electron magnetic field. So you can, the time period is constant as it goes around. And if you keep changing this so that every time it gets a kick when it crosses this, the AC frequency will remain the same because the time when it's coming around is the same. You can keep accelerating it till it eventually comes out. And when it comes out through this, it will have a high energy. and it will eventually come out through this. It will actually come out if we wait. If I wait another second. Satya, I'm almost getting to 1 hour. I hope you will allow me a little more time.
Sreerup, that's fine. That's fine.
Okay, thank you.
Yeah.
Okay, so let's just wait for it to come out. I think it will. Yes, it has come out. Okay, a new one has started. All right. So, well, here is a much bigger cyclotron built by Lawrence. You see Lawrence here, and this is his student whose name I have now forgotten. But you see the major. These two big objects are the magnetic field. They are two huge poles of a big electromagnet. You see, this is the superstructure holding it. And this is the world's largest cyclotron. It's at Triumph in Vancouver, and it can accelerate protons to 520 mega electron volts, which is more than half of its mass. So these are really highly relativistic protons. And the scale is fixed by this guy who is doing some repairs inside. Okay, he's wearing all this protective equipment, not for viruses, but because of the possible radiation, residual radiation and all of that. Okay. The other thing which people devised was that instead of the cyclotron, you could also devise something called a linear accelerator. So essentially, you have a proton source, and the proton simply goes across these little jumps, and there's a AC field, so that the field gives it the right acceleration from positive to negative at every time. And as the particle moves faster and faster, you make these tubes longer and longer, so they travel the same distance through all of them. And therefore, the particle keeps getting accelerated to higher and higher energies, and eventually hits the target. Okay, so unlike the cyclotron, this is limited only by logistics, since you can just keep on increasing the spacing. So you make it longer and longer, and you would get more and more energy. And so the Stanford Linear Accelerator, built in 1962, that LINAC is about 1.9 miles long. You see it here. These are the little buildings, and you see where it starts from, and it comes all the way to this building where the experiment happens. And by 1965, it had reached 1 GeV. So that's 1,000 MeV, which is more than the proton rest mass. Why am I telling you this story? Let's try to understand, go back and look at the proton structure. So in the top half, I'm showing you what would happen if the proton was a solid ball. And in the bottom half, I'm showing it was like 3 solid balls. So this is a model of a point proton. This is a model of a proton which contains 3 quarks inside. So let's look at the top one, and let's see what happens if you fire electrons at it. So this is a classical model, of course. So the electrons will bounce and go in different directions. And as the electron keeps going, I'm just assuming elastic collisions, you would see a pattern of electrons around it. So just look at the pattern. On the other hand, if the proton has 3 particles inside, now the electrons are exactly the same as before. But now you will see that the scattering pattern is different. You see one goes through and one bounces in different direction, one has a double bouncing, all sorts of different things are happening. So now if you look at this final pattern, in the 2 cases, they are clearly different. And from this difference, you can infer whether the what the inside looks like. So this experiment was worked out by these 3 gentlemen, Friedman, Taylor, and Kendall in 1969, and later they won the Nobel Prize for this. So one way of understanding the difference is to write down look at the particles scattered in different directions and parameterize that in terms of 2 numbers called structure functions. If the proton is a point, then W1 and W2 will be simply 1. So they will be at the top of the graph. You're plotting the energy of the electron on this side. So if the proton is a point, you will just get a constant like this. Now, if the proton was a jelly, remember, like the Thomson model, and the electron mostly would shoot through, then as the energy went up, then these W1 and W2 would keep falling, which just shows you the probability of no scattering, of the electron just going through. But when the experiment was actually done, they found that in the beginning, yes, the electron did behave a bit like a jelly, but then it became a constant like this one. So at about 1/3, this thing stabilized. So in some sense, at low energies, the electron was behaving like a jelly, but at high energies, it was behaving like 1/3 of a point particle. Very simple, Feynman said. You see Feynman here telling you that, look, the fact that it's leveling off at 1/3 simply tells you that there are 3 particles. You're looking at a bunch of 3 particles, and in the beginning, when you hit it with low energy, the whole thing shakes up a little bit and it behaves like a jelly. But when you hit it really hard, then you go inside and you hit one of the point particles, and what is then the behavior is just like scattering from a point particle. And you're getting 1/3 because you expected the whole thing to be one particle. So therefore, these must be the quarks. So therefore, there are 3 quarks. And of course, Feynman had this rivalry with Gell-Mann, so he didn't like the word quarks. He called them partons. We like both Gell-Mann and Feynman, so we call them the quark-parton model. So sometimes we call them quarks, sometimes we call them partons. We don't care. So here is our picture of the proton or the neutron. Well, this is really of a neutron. You see the positively charged red one is a positive quark, the up quark, and these are 2 negative quarks. And now the size of the quarks from the scattering experiment is about 0.01 femtometers. So we have gone down 10 orders of magnitude. We've gone to the 10 attometer scale. So now with the discovery of quarks in 1969, we had reached the attometer scale. Now a little more, the problem with a LINAC or a linear accelerator like SLAC is that electrons will be hitting the target once and that's the end of it. Okay, it comes straight and hits the target. You'll have to wait for another electron or another bunch of electrons to come. So people invented this nice device called the storage ring, in which you inject a bunch of particles. They come around and hit the target and keep going around. And every time it crosses the target, it hits the target once. So you can inject a bunch of electrons and eventually you can get it out. But the high flux, you can mimic it simply by reusing the same bunch of particles again and again. So therefore, you have not only improved, or you can get the energy you like, but you can get the energy of fairly high energy cosmic rays, not the really high energy ones. But what you could do is create a high flux simply by reusing the same bunch again and again. Then people had another bright idea that why you use a fixed target? Why not put 2 beams from either side and let them just go around and collide with each other? So every time the bunch goes around, you can see one bunch going around. Every time they go around, they are colliding here. So here's a collision. And then you would get twice the energy. Take the same beam and make it collide from both sides, and you would get twice the energy. And this is the colliding beam pattern, which is now followed in most accelerators. So in the 1970s to the 1990s, more and more quarks and some leptons were discovered at these high-energy colliding beam collider machines. And I hope my internet connection doesn't die. So the up, down, and strange UD and S quarks were discovered in 1969. These were the 3 suggested by Gell-Mann. In 1974, people discovered a 4th quark called the charmed quark. In 1977 came another one. So the size of this is sort of proportional. It's a cartoon of the size. It's not really the size, the mass. But these are more and more massive. The bottom quark was a bit more massive. And then came this giant. In 1994 came this giant discovery of the giant quark called the top quark. And now we have reason to believe there are no more quarks. And by the 1980s, we had a pretty complete picture of the elementary particles called the standard model. And then you have the quarks here, the upcharm, all of these here. There are the leptons corresponding 6 leptons. There are the WZ, gluon, and photon, which give you all of this. But you see the center is empty. And I'll come to that in a moment. In the 1990s, this was tested to 1 part in 1 lakh. So it's really very well tested, very nice model of how elementary particles behave. As I showed you, there's a hole in the middle of that graph and only one ingredient was missing. And with that, we close the modern times and I bring you to recent times. And in the recent times that people were looking for that hole, and it's a long story. So let me get into that now. So let me explain a little bit of the idea behind it. So here you see a system with rotational symmetry. It's a sphere. Sort of, it's supposed to be a sphere. It's a circle on your screen. But now I've set it rotating. Can you make out that it's rotating? I'm sure not. I can't make out that it's rotating. But it is rotating. So what does that tell you? That when it rotates, every rotational position is the same. You can't make it out. So in mathematical language, we say it's invariant under rotation. When it rotates, nothing changes. It's exactly the same. All right, let me distort it a little bit. Now it doesn't have rotational symmetry. As you know, you may have noticed, I've sort of distorted a little. It's become a little fat in the center. Now let me set it rotating. Can you make out that it's rotating? Yes, of course you can. Okay. So now that you see that invariance under rotation has gone. So in some sense, you can have a symmetry and that corresponds to an invariance, and then that goes, this is under rotations. Now let's look at this same ball and assume that I put it in the jaws of a vice and I press it. Say it's a rubber ball. What will happen? You've seen, it comes back. Take a rubber ball, press it like that, so it will come back and the symmetry comes back. So if the symmetry is a sort of sacred principle, the symmetry will come back. But of course, when you press a rubber ball, you don't talk in terms of symmetry. You simply say there's an elastic force which is making the rubber ball come back to its original shape. So here is a way in which you can understand a force in terms of a symmetry. There is really no difference. The agency which causes a symmetry to happen is also called a force. We understand it as a force. Now, similar, but of course more complicated theories based on symmetries can explain all the fundamental forces in nature. So you have the electromagnetic interactions, the strong interactions, the weak interactions, gravity itself, and the corresponding symmetries are the QED symmetry, the QCD symmetry, the Glashow-Salam-Weinberg symmetry, and for gravity, of course, it's the general symmetry theory of relativity. And in all of these, let me take you to one step further. These are good symmetries except for the weak interactions. Let's come back to this ball. Now, suppose there was a little bit of an extrusion from this ball. Of course, it would break the rotation symmetry because if now you set it rotating, you would see the rotation. So the symmetry will not permit this kind of extrusion to grow. This has to be a symmetric ball. It has to be a smooth ball. You can't allow these little things to grow on it. However, similarly, you have particle masses. If you give masses to particles, they break this gauge, something called the gauge symmetry, which is what all these theories are based on. And the gauge symmetry does not permit a mass. Exactly like the elastic thing cannot grow this pimple on it. And therefore, you have this gauge symmetry. Therefore, you have massless photons, electromagnetic waves, which we are familiar with. Okay, so let me just show you that for the electromagnetism and strong interactions and gravity, the carriers are indeed massless and the gauge symmetry is not broken. But for the weak interactions, for the Glashow-Weinberg theory, the particles do have masses. And they have very high masses, in fact, 86 and 97 times the proton mass. And the result is that, therefore, we have to understand that the symmetry has been broken. It's been lost somehow. Well, we can understand that in the following way. Imagine that you've taken this rubber ball, which I've been showing you, and you immerse it in liquid nitrogen. After that, when you take it out, the ball has lost its elasticity. Now you put it in a vise and you press it. Okay, it stays like that. It doesn't come back. What you say is either you say that the elastic property is lost, or that because of the cooling, the sharp cooling, the symmetry was spontaneously broken. I mean, you didn't do anything by hand, you just cooled it. So the symmetry is spontaneously broken. And of course, for a material, we would say the elastic property is lost. So in some sense, that force is gone. And now, what we would say about the rubber, we would say the rubber of the ball is no longer the same material. It's undergone a phase transition. Okay. And now if it grows a pimple, fine, it'll stay. No problem. That this new material is no longer an elastic material. It's a sort of dough kind of material. You can make extrusions. And now if we translate this similarly, instead of the rubber ball, we have the universe. And the gauge invariance was the symmetry there and causing this weak interaction force. Now that symmetry has been spontaneously broken because we know that the universe cooled. After the Big Bang, the universe cooled down. And therefore masses appeared because of a phase transition. However, for the ball, it was the rubber of the ball. For the universe, what was it? You need something to undergo the phase transition. There has to be some rubber equivalent in the universe. So the idea here is that the entire universe is actually immersed in a massless, spinless field. Forget about the technicalities. There was a field. Now this field underwent a phase transition when the universe cooled below about 10 to the 15 kelvins. And at that point, because of this phase transition, the gauge symmetry was broken and this field acquired a mass. And when it acquired a mass, this actually gave mass to all of the other objects and it allowed structures to form. So because of this, these masses, see, massless particles move at the speed of light. That's what relativity tells us. And therefore, if every particle is flying away from every other particle at the speed of light, they can never come together and form structures. So it is because of this electroweak phase transition that we are able to see structures in the universe. You see this is from the Hubble Space Telescope, are deep structures. Here is a cartoon of our solar system, all these structures. And therefore, in the solar system, this object is the Earth here. And we are sitting somewhere here. The structures which are all around you, of yourself and myself, we are all due to this phase transition. Now, I'm sure those who are not aware of this will ask, why should we believe such a bizarre theory? You will have the same skepticism as on the face of this gentleman. The reason is that this was pointed out by Peter Higgs in 1964. If this theory is correct, there should be a spinless elementary particle with a mass somewhere between 3 times the proton mass and 1,050 times the proton mass. And in Higgs's honor, it was called the Higgs boson. So Higgs, when he proposed this in 1964, was a young man, you see here, young man with sharp eyes. And the properties of this Higgs boson were very cleanly defined. But it took 8 years to find it, from 1964 to 2012. And in 2012, it was found. In 2013, Higgs received the Nobel Prize. His appearance had changed a little bit since then, as you see. But of course, the eyes are still as piercing as ever. And here I show you a picture. Many of you have seen this live. On July 4th of 2012, this was announced at CERN. You see in the middle, this gentleman with his arm upraised, saying Rolf Hoyer, who was the Director General of CERN at that time, raising his hand and saying, gentlemen, I think we have it. It's a great moment in the history of particle physics. So the Higgs boson was the last ingredient in the Standard Model, and finding it has made the model complete. So now it sits right in the center. It gives mass to all the others. Of course, to achieve this goal, a tremendous experimental effort was needed. So let me tell you a little about what this LHC was, which made the discovery. It's a giant proton-proton collider operating at 13 TeV, and it can probe structures at the quark size about 0.2 attometers. Here is a picture of the LHC tunnel as it goes around. In fact, you can drive a scooter around this. A man would be about this height from here. It's a great tunnel. It goes around 27 kilometers. The whole thing is buried. You see, this tunnel here is buried 100 meters below the ground. So you have to take several lifts to go down to actually work on the experiment. And some amusing facts about the LHC very quickly. When it runs, it consumes as much power as a medium-sized European town. Each beam can melt 500 kg of copper. That's the amount of energy which goes into it when it runs. The LHC vacuum, so remember I started talking about the vacuum, is about 100 times more thin than the space in which a communication satellite moves. LHC magnetic fields are 100,000 times, a lakh times the Earth's magnetic field. LHC magnets use 7 lakh liters of liquid helium and 12 lakh liters of liquid nitrogen. The temperature inside is 1.9 Kelvin, which is less than the temperature of the universe, of outer space, which we know to be 2.73 Kelvin. The LHC protons have so much energy that it's like a flying mosquito. So if one LHC proton actually hit you, you would feel it like a mosquito coming and settling on you. The LHC optical grid at 1.5 GB can eventually, I think one day it's beginning to happen, will eventually make the internet 300 times faster. So that's for those who are not interested in physics but are interested in downloading movies. That will actually also happen. In fact, the LHC is the biggest scientific experiment ever. It has probably now been surpassed if you take the totality of COVID research around the world, but otherwise it's the biggest single scientific experiment ever. And the LHC has just barely started searching. The search has just started. It has run for about 8 years. It has found the Higgs boson. It hasn't found anything else, but it's like a small boy who has begun to dig a hole in the earth. And over the years, it will going to run all the way till 2040 or maybe beyond. So this hole is going to go very deep. It's going to, and hopefully when we dig deeper, please stay tuned for more and more discoveries from the LHC. So on this note, I will finish with a quotation from the Roman emperor philosopher Marcus Aurelius, his famous book Meditations. The quotation says, "Look within. Within is the fountain of truth, and it will ever bubble out if thou wilt ever dig." So as we do dig inside, deeper and deeper inside matter, inside the atom, inside the nucleus, and so on, hopefully we will uncover more and more about the ultimate truth of the universe. On that note, I'll end this note. Thank you so much for your patience in listening to that all.
Thank you very much, Sreerup.
Okay.
So I remember I wrote a simple phrase saying that Sreerup, for those of you who know, is the master storyteller of high energy physics. Maybe I should change that to say he's a real magician of particle physics. So it's fantastic, and
Thank you, sir.
it was such a nice, I mean, if I can use that word, story to listen to, and beautiful animations and beautiful pictures, and you really covered a vast material, vast scales, and also ending the kind of things that are waiting to be kind of fathomed or discovered by the younger scientists on the Zoom call today. And I'm sure there are quite a few very interesting questions, especially coming from a more younger,
Yes,
if I can notice.
yes.
So I will try to take up. I mean, there are questions both on Zoom as well as on YouTube channel. So in case some of you on Zoom, if you have not yet raised your hand, please raise your hand and keep it that way. I will take one question at a time by unmuting you. Okay, so I am coming to Sarthak. So please go ahead and ask your question.
Yeah, a very nice talk. I
Thank
want
you.
to know, does the question make sense if we ask what is the size of an electron, or why don't we have a talk about that?
Okay, so the answer is that see, the electron, we believe, or understanding of electron is that it's a point particle. So therefore, it is smaller than anything we are aware of. That's the way we model an electron. However, you must understand that when you go to these very small sizes, you can't think of the classical picture anymore. So what you have to think of is the quantum picture. And in the quantum picture, there is you can't find a size exactly. What you have a sort of fuzzy picture. Now, in this fuzz, the electron is also the electron, and it's sort of a little area of influence around it is also around a femtometer. Okay, or and so on. So in fact, so that's the problem with quantum mechanics, that you can't, that all the pictures I've shown you of round balls and so on, these are sort of semi-classical pictures. The real electron is a sort of fuzzy thing, and in some senses it behaves like a point particle, but there are other places where it behaves like a sort of fuzzy object, like a wave in some sense. So I can't give you a definite answer to your question. For most practical purposes, the electron is a point particle. But if you really go very close to the electron, then it has some other behavior. So anyway, it's a very interesting question which you asked.
Yeah,
Thank you.
that's okay. We'll take one more, and then keep switching between the two platforms.
Sure.
Anyway,
Sure.
Okay, we are going to take the next question from Upamanyu Maitra.
Yes.
Okay, please go ahead.
Hi, good evening, sir. So you said that Higgs had predicted in his original paper that the Higgs mass would be between 3 and 1050 proton masses. Did he have any particular reasons for doing so, considering that Higgs mass is something that's still keeping us busy these days?
So, Upamanyu, since I know that you will understand a more technical answer, I will give you both the technical and the non-technical answer. So, of course, let me mention that Higgs, in his paper, he only predicted there would be such a particle. He didn't actually predict the mass. Okay. So I sort of telescoped various papers written at that time. The mass prediction. So the 3 GeV limit came because at that time there were experiments at 3 GeV, which told you that the Higgs had not been discovered. So you knew it had to be heavier than 3 GeV. The 1050 GeV, it comes from a consideration which you will understand, but everyone, it's called unitarity. So basically what would happen is that the quantum field theory of weak interactions, of which Higgs is a part, would develop an internal inconsistency if the Higgs was more than 1050. So that was sort of about 1050 times the proton mass. So that was in some sense an upper limit, because of course you introduced the Higgs so that the theory would be consistent. So that was the reason. And of course you know what unitarity is, Upamanyu. So in your case, that's the answer to your question. I can tell you more sometime later, because of course I can always talk to you later. Thank you.
Okay. Abhimanyu also made me to kind of say this. So the guys who are asking questions, if you wish, you can even open your, you can show your face by enabling your camera.
It's always nice to see a face.
Yeah, see the face, right? Yes. I wanted to say that. Okay, so we are coming to what is written as KK. I don't know who he or she is, but yes, you can go ahead and ask. 1 minute. For some reason yeah. Can you go ahead? KK.
Hello sir.
Hello.
I wanted to ask about the part where you said that the universe underwent a phase transition and the spontaneous symmetry was broken and Higgs particle gave masses. That part I'm not clear. As far as I understand, Higgs is a mathematical construct, right?
No. It's not a mathematical construct. No. It's a real particle. It's a real field.
That I understand. It's a real field, but the phase transition part, I'm not.
Yes. So the phase, ultimately, what happens? You have other phase transitions in the world. Okay. There's a phase transition when water becomes ice, when water becomes steam. There's a magnetic phase transition. So what happens in the phase transition is that the properties of the material change. Okay. So you say the properties of the Higgs field change. Now, of course, when you have a phase transition, you want to model it mathematically. So there are mathematical models for the phase transition of water, for the magnetic phase transition, for the superconducting phase transition, and so on. So the mathematics you see is just a mathematical model of the Higgs phase transition, which was a real physical phase transition which happened. So the Higgs has a self-interaction. Essentially, at some point, the phase self-interaction, okay, self-interaction means the Higgs part field interacts with itself. This is a strange thing, but yes, it does. It basically tells you that, light, for example, doesn't interact with itself. So 2 photons will go through each other undisturbed. But 2 Higgs particles will not. They will interact with each other. So they will scatter from each other. So because of this, there is a point, there's an energy scale, which is equivalent to temperature, because as you cool down, the energy scale goes down, where the scattering of the Higgs is in a sense stronger than the velocity or the mass or the inertia of that. That's a sort of classical picture. But when this interaction scale becomes stronger, at that point, the property of the Higgs field changes. At that point, a mass originates where you didn't have it before. Okay, the energy behavior changes. And when that phase transition occurs, the Higgs itself acquires a mass. Now, all the other particles which acquire mass acquire it because of their interaction with the Higgs. So it's very easy to understand it as you think of different particles. The Higgs particles as clinging to the other particles. So imagine there is an electron. So the electron, whole bunch of virtual Higgs particles will cling to the electron. So when the electron moves, it's like a man with a heavy bunch of guys sitting on his back. So the electron moves slowly. So you think that it's not moving at the speed of light. It has acquired a mass. Now the electron doesn't interact too strongly with the Higgs. So it doesn't have too much of a mass. But a top quark, on the other hand, is much more massive because it interacts much more strongly with the Higgs. So it's like the top quark has a whole bunch of other people also on its back. So it moves much more slowly, which means you think of it as much more heavy. The photon doesn't interact with the Higgs at all. The Higgs is neutral, so it doesn't interact with the photon, which is after all the electromagnetic field. So therefore, when the photon moves, it keeps moving at the speed of light. So it doesn't get a mass. So that's the kind of picture. So the Higgs first acquired mass because the properties of the field change. So that's the nature of the Higgs field, the innate nature. It's such that when the energy level goes down below, the nature of the field changes. And then with this mass, it sort of gave this mass to all the others. That's the picture we have.
Okay. There are quite a few questions still left on Zoom, but I'm coming back. Please hold on. Let me come towards YouTube. Of course, a huge number of questions. I request the speaker to see how many we can kind of cover them.
So
Uh,
I'm happy to keep answering, but you must be having a time limit. So
yeah, not a problem. Okay, so
your problem.
I'm also making sure some of these INO students, they can stay, hold on for some time. I'm taking Vishal Naik, how they calculated radius and mass of these particles, and is there an experiment which confirm?
So radius and mass, of course, will be calculated from the scattering data. So just as the Rutherford experiment, you could conclude that there was a size of a proton beyond which, if you saw that, the scattering pattern would change. So everything comes by fitting it to the scattering data. Essentially, what you do is that you know the nature of the force, which is the electromagnetic force for most of the scattering, or the nuclear force. You have a model of that. Model it, compare your model with different sizes. The size which fits the scattering data is the size. The mass, of course, the particle will recoil when you hit it. The recoil velocity and so on will, of course, show up again in the scattered particle. So from the scattering data, the mass and size of the particle which fits it. And once again, remember that these are all point particles like the electron. The size is a not very well defined thing. So it's not, so don't think of those hard balls. They're all fuzzy balls. Okay. So size is just a parameter which explains the rough sphere of influence of the particle.
Okay.
Okay.
So we have Jyoti Ru. What is meant by the radius of this quark? Is this assumed like a solid ball? I think you answered.
I've just answered this.
Yeah, so because it is in that kind
Yes,
of, YouTube
yes.
questions are kind of timed at your
Yes.
station. So
It's okay. If the question is repeated, I've already answered it. Let's try to answer the other ones.
As photon has no charge, how it interact between proton and electron?
Photon has no charge, but it's the electromagnetic field. So the electromagnetic field interacts with all charged particles. That's the definition of charge. Anything which interacts with a charged particle is called, interacts with the photon is called a charge. So it's a sort of circular question.
There is Hardik. Hardik has a question. Is it any possibility to find independent quarks by astrophysics?
The first one, I should tell you one thing which I have not told you. There is a well-known understanding now that you cannot separate out the quarks. They will either sit as a quark-anti-quark pair, or as a set of 3 quarks, or sometimes 4 or 5 quarks, which are unstable. But you can't separate out individual quarks. So even if you have astrophysical experiments happening at very high energy, you are never going to be able to separate out those quarks. So it's an interesting feature of quarks, perhaps a bit frustrating, but everything about quarks has to be inferred from their bound states.
Sreerup, another question. Maybe
yes.
You can publicize this. Sir, if you have written any book, please mention here.
Well, I have not written a book on elementary particle physics, unfortunately. I've written a rather technical book, which is called Particle Physics of Brain Worlds and Extra Dimensions, with my colleague, K. Sridhar. It's been published by Cambridge University Press under monographs in mathematical physics. It's a book for specialists, I'm afraid. It's very technical. But I am in the process of writing a book. Maybe I'll tell you this part because I've already signed the contract. Springer will be publishing a short book of mine, which is called The Early History of Particle Physics in India. So Satya and a few other people here, you have heard me give a talk on this. Yeah. So now I will be writing a book. Of course, we'll have a little more of details on that. Okay. So that maybe next year that book will come out.
That's great, Sreerup. That is an announcement. And,
yes,
so,
it's an announcement.
So it's congratulations. Yeah, we are all looking forward to seeing that in print. Okay, so very nice. Okay, then let me see. Okay, Mani Murugan, sir, briefly explain what a Higgs boson is in layman's language. Of course, I think I'm not sure you want to.
Sorry. Well, let me give you one example. Think of, as I gave you the example of the Higgs as having this sticky nature. So it's like it sticks to a bunch of Higgses stick to an electron and give it the mass. A bunch of electrons stick to of Higgses stick to a top quark and give it a lot of mass. Well, if you have a sticky thing like that, they can also stick together themselves and form a sticky ball. That is the Higgs boson.
Okay.
It's an analogy. Okay, I mean I can't explain it better.
Let me come back to take a few more questions from Zoom. There's a question from, okay, let me first unmute. Okay. This is BBC Tripathi.
Yes.
Yeah, can you please ask your question?
Yes, of course. Namaskar, sir. It was a really enlightening experience watching the lecture of yours.
Thank you.
I have a very simple question. I mean, it could not be right now so much relevant to standard model of particle physics, but a few years ago, probably in 2012, when the 13 TeV experiment was going on, graviton was in a hype basically, and I did a little bit of study on gravitons. But as per your lecture, I have understood that since we have now been able to explain the in GTR, we understand that the gravity is nothing but the curvature of space-time, and then using the, I mean, when we talk about gravitating interaction between two mass particles, like there are 2 point particles with masses, and when they have a force between them or a field, that we call that gravity. So is there any relevance to graviton as a field of research or something? Like, should scientists be searching for it?
All right. So the graviton is certainly we should be searching for it. Let's put it like this. So general relativity, of course, is a theory of the gravitational force, and general relativity it has its own specific features. But general relativity, you can cast it like a gauge theory, especially when the interaction is not very strong. So it's reasonably weak around the Earth and so on. So you can put it like a gauge theory. And then, of course, there will be waves in gravity, which are similar to electromagnetic waves. Now, these were predicted in long back when Einstein gave his theory, but we have looked at it for years, and we found it only recently, as you know, with the LIGO experiment, discovered the gravitational waves. Now, once you have waves, then you see that they have the wave property. And if you believe in quantum mechanics, then of course if you believe that the world is quantum mechanical, then the waves, just like the electromagnetic waves are quantized and you have protons, the gravitational waves should be quantized and you will have gravitons. Okay.
Right.
Now, so therefore, it is certainly, and since we do believe that quantum mechanics works everywhere, then there should be gravitons. They are not easy to look for, but also at the theoretical level, there is a problem with gravitational waves and gravitons themselves, because getting a quantum theory of gravity is not easy. And people have been working, but there are technical problems which have almost proved insurmountable. So till now, nobody has a quantum theory of gravity which is acceptable to everyone. Okay. So there's both a theoretical and an experimental thing. Experimental is easier. You make your experiment more and more sensitive. There are experiments by which you could search for a quantum for a graviton, and those are being pursued. I must warn you, they were very, very difficult experiments.
Right. Yes. So one more, just a quick question again, because as you said that when at a certain time in the process of evolution of our universe, the gauge symmetry was broken for the Higgs field, and the Higgs boson came out that actually gave mass to everything else. So what was before that? Like, did the Higgs boson did not exist? Did it not exist before the symmetry?
The Higgs boson existed from the beginning. Just after the Big Bang, the Higgs boson existed. All the particles also existed. They were created at that point. And then, of course, but the point is that they were all massless. So you had a kind of soup where all the particles were flying around at the speed of light. And nobody was touching it. No bound states can be formed. Nobody was coming close, because, two particles which are moving at the speed of light, their relative speed is also that of light. That's what relativity tells us. So therefore, nothing could come together. After this phase transition, so you just had a soup of particles flying around. And then when the Higgs acquired its mass, it also gave mass to the others. So the particles slowed down, and then they could form bound states catching each other. That's the picture.
That's it. Okay, great. Nice explanation. Thank you very much.
Thank you.
Okay, we have another question from Unni. Says, sir, you said about phase transition in our universe. Is there any connection this with the existence of dark matter?
I don't know. I think there may be, because we feel that we certainly know that the dark matter in the universe has mass because it has a gravitational interaction. The only way we've been able to see dark matter, it's dark because we can't see it, but it has gravitational interaction. That's why we know it's there, and therefore, if it has gravitational interactions, it must be having mass. So if it has mass, it's very likely that it acquired mass through the same mechanism as the Higgs boson gave mass to the other particles, if the dark matter is a particle. But till we know more about dark matter, I can't give you a definitive answer. Most of the theories of dark matter assume that it also acquired mass through the Higgs transition, but you never know. You never know.
That's nice. Just a minute. So why we have the same number of quarks as many they are leptons?
I wish I knew. It's a very interesting and intriguing question. Why do we have basically we have three pairs of quarks, the up and down, the charm and strange, and the top and bottom. They seem to be heavier copies of each other. The leptons also seem to be heavier copies of each other. So there is this question which people have been asking since the 1970s. Are we seeing a repetition of this thing? Is there substructure inside the quarks and leptons? And of course, let me just tell you this, because there's a very famous Indian physicist involved in that, in two people from the subcontinent. In 1974, Jogesh Pati, who is Indian from Orissa, and Abdul Salam, who was Pakistani from Hyderabad in Pakistan, they developed this theory of preons. But the preons are particles which are smaller than quarks and leptons, and with just about, I think, 2 or 3 preons, they could take all of the, you could just put them all together and create all the quarks and leptons. Now, these ideas have been floating around, but we don't have any evidence for them yet. Maybe in the future, one of you will find it. I don't know. But that idea has certainly been there. And the fact that there is more, that there are repetition and there are similar things, we don't really understand the reason. That's what we have found. I mean, perhaps there's substructure, perhaps there's not. Perhaps the repetition is due to some other reason, which also people have theories about, but we don't really know.
Yeah, you did say a little bit what is in future, but there is also a specific question if you want to add something more. What are the future aspects of particle physics we can look for?
Well, I have to now put a tilak and sit with a parrot, and I can tell you what will be discovered in the future. But I am hoping, of course, that we will be, there are many things about the standard model which we don't understand. And one of the biggest is this mystery of this electroweak symmetry breaking, why it happened. And how this happened would be understood perhaps by some of the experiments from the LHC. So I'm hoping it will happen. Okay. So that's one of the things. We may discover new particles. If we do that, it would be very exciting. I'm sure we will discover new particles, but what they will be and what the nature is, I can't quite tell. We have to wait and see. So just 1 minute. Just one. I'll take a break for just 1 minute.
Yeah, sure. Please go ahead. So can I?
Sorry. Please go ahead.
Okay. Now let me see if I can about the.
Sorry, I lost you.
Yeah. Okay. So there's a question from Zones about the size of electrons / protons. Is there a quantum mechanical way to determine the size of an elementary particle? Maybe using.
I think I've already answered that using the scattering data.
Scattering data.
Yeah, you look at the you calculate the scattering cross section in terms of quantum mechanics.
Yes.
And the size and the mass, all these will come as parameters, and that fit it to the data, you will know the answer.
Okay. There's a question from Sadashiv Sahu.
Yes.
Why cosmic ray flux fall as power law?
Well, the energy, most of the cosmic ray flux is due to the sun. Sun has a certain energy which is low. The higher the energy goes, they come from these rare events, like, as I said, supermassive black holes, merging galaxies, quasars, all kinds of, but these events are very, very rare. You must remember that when things collide in the universe is extremely spread out. Okay, particles that by now, since the Big Bang, it's been spread out to high. So these things happen only once in a while, and they are very, very much spread out across the universe. So therefore, the number of such events is very small. And when you have to have particles coming from those, remember that they are spread out in all directions. So a very small part is intercepted by the Earth, which itself is very small. So if you have very few particles, you call that a small flux. That's the answer.
Okay.
Rare events and very far away.
Another question: how can we know the charge of tin nucleus, SN nucleus from X-ray spectrum?
So you need to go back to your Bohr theory of the atom. You can calculate the energy of the electron levels in terms of the nuclear charge. Okay, you start with the Coulomb theory. And once you know the electron levels, then you can find out the difference between two electron levels. So look at the X-ray spectra and measure the energy, and that will tell you what the charge is. But the rest is all in terms of constants like electron mass and charge and so on, and H bar and so on, which you know.
Okay, I thought this was answered, but I'm just in case I'm missing. What is meant? This is by Jyotirup. What is meant by the radius of this quark? Is it assumed to be a solid ball, or is it decided by a point?
Yes, I think I've answered this already.
This is covered already.
Yes, yes. Let's
can you explain? Okay, layman's language. We have same number of quarks. Picture of electron. What is? Okay, I thought we can now go. So just see if we have any more questions. Here again, something about gravity. Hardik says, sir, as we synthesized gravity to use concept of circular motion, so take that kind of analog. Can we define a graviton or gravity by concept of spin?
Well, I think they are separate concepts. Spin is an intrinsic property of all these particles. Okay, it's an angular momentum carried by them. Remember, they are point particles. So a point is not a rotating thing. Okay, it's just an intrinsic amount of angular momentum it carries. The graviton has a spin of 2 units of charge. You know, the electron has a unit of half a unit of charge of angular momentum. Now, spin is an intrinsic property of particles. It's as fundamental a quantum as momentum or charge or energy and so on. So the model of one thing going around another is an old classical model. Okay, so I'm not sure you could model it like that. It's a purely quantum mechanical effect, and you should just think of it as an intrinsic property of the particle.
Okay, I see another question, but probably if you don't mind. Okay, so please discuss a bit on the recent progress of T2K experiment. But instead of you taking it, I would refer to lecture by Urjit Yagnik, which he gave on this very same series. And if you go and look at his video, probably you will get an answer.
I can see.
You want to add anything?
I can see a few names on the screen who are far more qualified to answer this than I do. But yes, so I know what the T2 experiment is, but maybe I'll pass this question.
Okay.
Yes.
Okay, Sreerup, I do have a few more questions, but I think for taking, the fact that it is already at 7:45, I think I would like once again to thank on behalf of all the participants for accepting our invitation and giving such a wonderful talk. And I'm sure some of them who has still some questions, if they see your video through once again, I'm sure many of them concepts, I hope they'll get them right. So with that, let me once again thank you and close today's session. If you have anything to say.
Thank you all.
Yeah. Okay.
No.
Thank you very much then. Please be back tomorrow at 6 o'clock. As I already announced, Professor Unni Krishnan's lecture is going to be on the same series tomorrow at 6 p.m. So until then, take care and stay safe. Thank you very much.